As we saw in the last chapter, this original oscillator circuit here was not working too well. It was actually spinning on the wrong frequency, and that usually means that the crystal is not loaded as it should. And if we look to this graph here, we show how a crystal normally is working. And as you can see here, the crystal has a center frequency where it has the lowest impedance. And it also has a parallel resonance frequency, which is the frequency where it has the highest point of inductance relative to capacitance. And the crystal's nature is that it's both capacitive and it's inductive. And that means that the crystal that is coupled like you have here both have the input and the output impedance of this circuit to take in mind when you think of the load that actually coupled to this crystal. And the feedback resistor that you have down here is also something you have to consider, as it's shorting this gate here. And normally when you have a crystal in a circuit like this, you have some capacitance and some resistors that is putting load on the crystal so that you force it to act within these boundaries. As we saw in the last video, this crystal was spinning somewhat over here. The frequency was about 3 times as high as it should be. And my brother, who works as an electronic design engineer, come up with this design from the internet. And this is something I've actually seen before, and it's a common way to express a serious resonant circuit, as this should be. And it's very easy to convert this one into this one, as it uses the same logic gates. And although this is not an ideal circuit, you will get a square wave out of this. What is problematic with this kind of circuit is that you will almost never get a perfect square with an even 50% duty cycle out of this. And this is where this kind of circuit works the best, which uses a Smith trigger. And also the CMOS gates has a much higher impedance on the input than a TTL kind of gate. So that means that the crystal resonance circuit will be much easier, because you can almost ignore what the gate themselves brings to the table. And it also has a Schmitt trigger on the output, and a Schmitt trigger work kind of like this. It acts that you have a high trigger point and a low trigger point, and when the pulse is rising and reaches the high trigger point, it will trigger the circuit, and when it drops, it won't switch the output until it reaches the lowest trigger point, and so on. So a Smith trigger is really the cleaning lady of the circuits. It cleans almost every kind of pulse into a square wave. And this is also represented in actually the symbols for the Smith trigger, which is a hysteresis symbol. So it means that you have some delta between the high and the low trigger point, and the output does not exist between these boundaries. It switches when it comes to this, and it switches when it comes to this. Whereas this circuit here, and even though it's a logic gate, it acts as a follower, because there is a linear function between the input and the output, and it's only in our minds that we have set the boundaries for high and low on this kind of circuits, whereas the Smith trigger has an output that does not allow the output to stay in an undefined state. So this kind of oscillator has an advantage over the TTL gate kind of oscillator. And what we will see in the circuit is that we have actually modified this. This is the original circuit from the schematics, and this is the schematic from the internet. And I have done some testing on this, and I have modified the board like this, as we will see later on in the video. And I put on these two resistors, and I also put on this extra capacitor here. And the circuit now seems to be spinning quite okay on the right frequency. But what we should have done in the beginning is actually to buy one of those. This is not a crystal, as many called this circuit. This is oscillator. It's a finished oscillator, and they have a TTL compatible output. So you feed this with 5 volt and an enable pin, and you get a square wave with the desired frequency out of this box. And here you can see on eBay you can actually buy 10 pieces of this crystal with the frequency we need for about $9. And I think, even though I have got this circuit to work, I will eventually switch it into one of these, because this is a much more future-proof circuit. As a crystal oscillator as the one we have here, it can be prone to frequency drift and instabilities, and it's also possible that even though we have got it to work, there are some borderline cases where this will drift out and you actually come to another part and maybe it switches again to resonance on a higher frequency, as we saw in the start. This will be the permanent solution, I think, but until then we will try to get the circuit working with this one. Yes, as we can see here, I have done the mod straight on the PCB. I have broken the connection between the two hex inverters, and I've connected a 100 nano capacitor from one side to the other, and I also connected this capacitor and this resistor as shown in the schematics. And here is the decoupling capacitor from ground to one leg of the crystal oscillator. And this is the whole mod that is done to this board regarding the oscillator. And I do have some concerns about this, because I don't have any way of measuring this accurately enough. If there are some small variations in this frequency, I will not be able to do a proper measurement with the scope, because these fluctuations is very difficult to observe with the scope. But the clock is ticking on the frequency we want, mostly at least. So this will be it for now for the modification of the oscillator circuit. Yeah, as you can see of this screenshot from the oscilloscope, it was not quite what we hoped for. If you see the red ring, you can see that the oscillator is spinning on 14.3 MHz, so we can claim that a victory. But if you see on the picture on the scope, you can see that you have this slight shadowing pointed to by the arrows. And as you can see, some of this is on one side of the wave, and sometimes it's on the other side of the wave. And that actually points us to believe that there are some frequency drift on this oscillator. But let's not jump to conclusions just yet. Let's see if we can get some picture on the video output. Yes, and this is the board as it is now with the redesigned circuit. And as you can see, I've changed the eproms or EEPROMs with eproms with the ZX Spectrum diagnostic ROM as made by Phil Ruston, and this is the 1.45 version, and I split it into two files and burnt it into two 64K EEPROM chips. And this diagram, I have read the instructions, but I have no ZX Spectrum to test them on. But as I understand it, this should make some text on the screen. There should be some flashes in the border and on the screen to indicate if there's something wrong with the memory chips and so on. And I've also changed the CPU from the last time, but the CPU that was applied was probably working okay, but I've changed it anyway. This is an old genuine C-Log Z80 from back in the day. But let's test to see if we can get something on the screen. I will connect the my trusty LG TV to a SCART connector and connect it to the composite video and see what we get. And what do you know? Much to my surprise, there actually now was some recognizable signs on the screen, and the screen was flickering. I cannot read the letters, but there clearly are some program piece executing on this computer, and now you can see the border is flashing and the test is actually showing, and you can read some test bad bits and something behind the garbled screen. And the garbled screen could be from something that's defect in the memory output registers. We actually tested all the memory chips in my Arduino DRAM video, and I've even tried some of these chips in another computer and they was working totally fine. So what will be the next step to debug the Leningrad? And we have to look into the video circuitry a bit more than we have so far. And the key to the video circuit is down here. You can actually see that the memory data is shifted into a shift register, and this is an 8-bit shift register. It has parallel data in and serial data out. And this is a 4-bit shift register, and these registers are shifting data to the screen right. And as you can see here, there are some multiplexing done to this signal to get these timings right. And you have some timings for the border, and you have some other timings that's driven by memory. And if we look into how the memory is organized, the memory map of the spectrum is made like this, and this is just a diagram that I got from the internet. The bottom 16K is the ROM routines, and then you have the screen memory, and on top of that you have the screen memory that's used for the color data information. And as we remember from the picture, there was some text in black and white in the bottom, and there was lots of garbled screen on top, and the screen data that was garbled was sometimes in color and sometimes not. But we have to look into how actually the data is decoded from the memory and written into the screen in the next episode. So this will end this episode, and thanks for watching. And then we know that there will be at least one more episode in this series. Please hit subscribe if you want to be notified when I post another video.